Hey, it's Dr. J. I'm back. Actually, I'm still here with more derivatives because I never left. I am starting over again with my numbering. So this will be example one of the second episode on derivatives. Kind of picking up right where we left off at the end of the last video. I did create a new function to sort of break the ice here in this addition. So we want to find the slope of the tangent line at x equals 3. And I'm going to call that part A. I do have a part B coming soon. I don't want to waste a lot of this nice clean board that I've prepared here for you on that. So now remember, we have the three definitions. So I will leave it up to you to decide how you want to do this. The slope of the tangent line is the derivative at 3. Yeah, so f prime of 3. So that's the limit as x approaches 3 of f of x minus f of 3 over x minus 3. Okay? That's option number one. Yeah. Option number two would be f prime of 3 would be the limit as h approaches 0 of f of 3 plus h minus f of 3 all over h. That would be my other option. My third option would be just to use a variable like x or a. Either way, this recipe always gives you the same result. Sometimes I do it using the letter A, and sometimes we do it with the letter X. But as I demonstrated in the last video, this third option gives you the same result, just with a different variable. Now, the only downside to using option 3 is you have to plug in x equals 3 or whatever value you have at the end. All right. So I'm going to leave that to you. I don't want to spend 30 minutes on the very first example, so I'm going to choose option 1. And I think through the course of this video, you will see these other options. You'll definitely see number 3. I use number 3 quite a bit. Number 2, not so much. I kind of see number 2 and 3. I don't know if you can see the pattern here. They're the identical calculation. The key difference between option 2 and option 3 is in option 2, you're stuck with whatever answer you plug in. Whatever answer you get, you're stuck with based on the input of x. Option number 3 is a little bit more flexible because if you want to plug in a different number for x, you can. All right. So when you choose option 1, watch what happens. The limit as x goes to 3 of 2x squared plus 6x minus 5 minus 2 times 3 squared plus 6 times 3 minus 5 all over x minus 3. So this is f of x, this is f of 3, and then this is x minus 3. Sometimes in my previous examples, I might have calculated this on Scratch. It's not a bad idea to do the Scratch work here, so you don't waste a bunch of valuable space here. So this is going to be 2 times 9 plus 18 minus 5 which is 18 plus 18 minus 5. That's 36 minus 5, which is 31. So there's my scratch work. Okay. So I've got -5 and -31. I am running out of space here, so that's going to be -36. So I'm combining the -31 and the -5 and getting -36, mainly because I'm about to run out of space here. And now I have the limit as x goes to 3. Let's go ahead and factor this. Looks like they're all divisible by 2. And then 18 is 3 times 6. I'm really cutting it close down here. And there it is. You always get a matching factor. It really makes the factoring a lot easier now that you are in calculus, because the denominator is giving you a clue as to what one of the factors in the numerator is going to be. You know, and if you know one of the factors is already going to be x minus 3, well, then it's pretty obvious that the other factor has to be x plus 6, because, you know, it has to multiply out to be -18. Okay, so the slope of the tangent line is, I'm just going to come around here and write my answer here. F prime of 3 is the limit as x approaches 3 of 2, x plus 6, which is equal to 2 times 3 plus 6, which is equal to 2 times 9, which is 18. Give it a little bit more breathing room here. So that's the answer to part A. The slope of the tangent line is 18. Okay, that tells you a lot about the graph, actually. It tells you that it's very, very steep. And it's increasing at a rate of 18 to 1, right? There's an invisible 1 underneath the 18. I don't write it, but you know 18 is actually 18 over 1. And so we know a little bit more about the shape of the graph. We know that it's increasing at a very steep, grade, I guess you could call it. If it was a road, it would be very, very steep. You wouldn't be able to drive up this road, right? I'm not going to get into what percentage that would represent, but it's very, very steep. Okay, now here's the problem with option 1, all right? And I chose option 1 intentionally. You know, I wanted to show you that the math is not that bad, right? It's just a little bit of basic algebra, right? With one little splash of calculus at the end. So it does have that going for it, right? It's pretty reasonable expectation of difficulty. But the downside is that you're fixed, right? You're locked in. You only have one answer. And so that's one of the reasons why I didn't tell you part B yet, because I want you to understand that sometimes knowing part B will help you make a better choice. So I hid part B from you. And I want to ask a secondary question. Find the value of x where the tangent line is horizontal. Yeah, that's the second question. Well, I know it's not here. Yeah, I know this is not the answer. 3 is not the value of x. That would make it horizontal. I already know that because this is definitely not horizontal. Yeah, I just said it's 18. It's very, very steep. Right? It's going up at a very rapid rate. Remember, horizontal, just a quick review of what horizontal means. It means the slope is 0. Yeah, like a constant function. Yeah, flat like this. This slope is definitely not 0. So we want to find x such that f prime of x is equal to 0. So I wish I would have chosen option 3 before. Sorry, you didn't choose that, so now you have to do it all over again. But you see the advantage? Had I chosen option 3, then I would have been able to take this result and simply solve for x. Now, I can't do that here because, look, my final answer doesn't have an x in it. You might try to come back to here and go, well, wait a minute, there's an x right here. Can't I just use that? Well, unfortunately, no, you can't, because this is not the derivative. This is the average rate of change, on a different interval near 3, right? And we don't know that our answer is going to be anywhere near 3. So option number 1 is quick. It's to the point. It gets you an answer very quickly. But then if you find out that you need more information, option number 1 is not the best. Option number 3 would have been better. So let's do f prime of x is the limit as x approaches, as h approaches, I'm doing option 3, as h approaches 0 of f of x plus h minus f of x all over h. All right. Keep this in mind, the 18, I can show you that we would have gotten 18 using option 3 as well. Yeah. All right. I'm going to need, just to save this, 2x squared plus 6x minus 5, just so I don't forget what that is. So I've got the limit as h approaches 0 of 2x plus h squared plus 6x plus h minus 5 minus all of this all over h. So that's the limit as h approaches 0 of 2x squared plus 4xh plus 2h squared plus 6x plus 6h minus 5 minus 2x squared minus 6x plus 5. Again, we've been doing this a lot. By the time you get this far in the homework, you hopefully will be an expert at that process. I intentionally use a lot of repetition, because seeing something once is typically not enough in this business. All right. This little box up here is just reminding me what my original function was. I have made the mistake of erasing it and then having to look through and scramble to find it again. So I just try to save it if I have the foresight to do that. Oh, my favorite part has just arrived. Cancel the 5s, cancel the 6x's, and cancel the 2x squareds. We divide them all by h. And there we go. Pretty typical result, right? We do have to finish the process, though. So this is the limit as h goes to 0 So that's going to be 4x plus 6. All right, 4x plus 6. So this is our f prime of x. Now, without actually making a big deal about it, remember the answer we had a minute ago? It was 18, right? Well, this is also going to give you 18, right? 4 times 3 is 12. 12 plus 6 is 18. It gives you 18 after you've done all the math, right? That's how option 3 works. In option 1, it just pops out the 18 kind of at the end of the process, right? So it's just slightly different avenue to get to the same result. So horizontal, we want to find when it's horizontal. We just set this thing equal to 0 and solve for x. So -6, -6, 4x equals -6. Here. I'm going to make it look a little cleaner for you guys. Horizontal, f prime is equal to 0. I want you to have a nice, clean step-by-step for something that we're going to be doing a lot of as we move forward. So I get 4x equals -6, divide by 4, simplify or reduce or whatever is appropriate. -6/4 is -3/2. Or you could say -1.5 would be okay as well. I'm just going to leave it as 3/2, -3/2. There you go. So at this point, the slope of the tangent line is horizontal. So what does that tell us about the graph, right? It tells us that it's either a maximum value or a minimum value. When the graph is horizontal, when the slope is horizontal, it means that you have reached either a maximum or a minimum. So a horizontal tangent line tells you one of these two things. All right. Now, based on the original graph, we knew that the leading coefficient was positive. Yeah. The leading coefficient was 2. So in this particular example, we know that it was a minimum. If the leading coefficient had been a negative number, so if that 2 had been -2 or some other negative number, then we would know it was a maximum. Being a business calculus class, as you can imagine, we're interested in minimizing some things, particularly cost, right? Labor, energy. We want to minimize those things, but we want to maximize revenue and profit. So let's get back to business. Given a revenue function, and I'm going to not spend a lot of time creating the function like I did in previous videos. I'm just going to assume that this revenue function has already been developed through research and analysis and observation or calculation, where X is the number of units. Sold. I'm going to give you both parts of the problem this time. So find the derivative. And then how many units must be sold? How many units must be sold for the revenue to be increasing because that's what we want, right? We want revenue to go up, increasing at a rate of $3 per unit. So this is what we call a revenue goal. Yeah, a revenue goal. We're setting a goal, right? We would like whatever this is, call it a widget or a gizmo or something. We would like to get to a point where every time we sell a gadget or a gadget, we're going to be increasing our revenue by $3 per unit. Where is that sweet spot, right? Now I just picked 3. There's nothing special about 3, but you set some kind of a goal, kind of a revenue goal, right? Well, first let's find the revenue of X. Yeah. Now, since we don't know what X is, we're clearly going to use option 3. So we're going to say the limit as H goes to 0 of R of X plus H minus R of X all over H. Right? When you don't know what your X is, you really are stuck with option 3, which I should say as we move through the rest of this section is going to be the most common method. All right, so that's the limit as H goes to 0 of negative 0.1 X plus H squared plus 165 X plus H. I better just save that. Minus, now copy the whole function, 0.1 X squared plus 165X all over H. All right, you're getting pretty good at this by now. That's going to be negative 0.1 X squared minus 0.2 XH minus 0.1 H squared. Now don't forget about that middle term, which is a 2, and then it's 2 times 0.1. Then you have 165X, 165H, and then this negative changes those signs, so you're going to get positive 0.1 X squared and negative 165X. All over H. Cancel. Oh, there we go. So the X squareds cancel and the 165's X's cancel. I almost canceled the wrong thing, but I caught myself. Negative 0.2 XH minus 0.1 H squared plus 165H. Divide these all by H. H is going to 0. So let's cancel the H's. And then you're going to get negative 0.2x plus 165. So first I cancel the denominator h's, and then I cancel the middle h by setting it equal to 0. So notice this whole middle term becomes 0 here. So it's just gone completely. So all you're left with is the first term, negative 0.2x, and the last term, positive 165. So this is your derivative. All right, that's the derivative of r, also known as r prime. Now, what's cool about this is because we did it this way, sort of the open-ended way, we don't really know what x is. X is a variable value, right? Now I can solve this by taking this equation and setting it equal to 3. So for part B, set r prime of x equal to 3. Now, of course, it's not always going to be 3. There's nothing special about it. It was just the revenue goal that I set in this problem. I think I picked 3. Why did I pick 3? I think I predicted that it would give me a nice number. I could have picked 6 or 5 or 4 or something, but I just wanted 3 to be nice. $3 a unit. That sounds like a good number. I think it comes out very nicely, so I'm going to solve this for x. Should be pretty quick. Negative 165, negative 165. So I got negative 0.2x equals negative 162. Right. And then I'm going to divide by negative 0.2. So I get a negative divided by a negative. I actually don't have my calculator handy, so that's going to be divided by 2/10, which is times 10 halves, which is 81 times 10, which is 810. This is how, your ancestors would have had to do it without their calculators. 0.2 is the same as 2/10. Then I flipped it to 10 halves. You could also just turn that into 5 as well. So you could have done 162 times 5, and that still would have given you 810. What I did is I went 162 divided by 2, and I got 81. And then I went 81 times 10. I did that because when I don't have a calculator, multiplying by 10 is actually easier than multiplying by 5. Right? But you still would have got the same answer. So 810 units. All right. I'm not going to draw like a super detailed graph of this, but I'm going to sort of lead into the next problem a little bit. Revenue kind of looks like this. So R is like Y, or RX, same thing. If you sell nothing, you make nothing. So revenue always starts at 0. Right? Pretty obvious when you look at the formula why revenue always starts at 0. If you plug in 0 for X, you get out 0 for Y. So this is our Y value. And then the revenue goes up, and then it comes back down. Yeah, just like the gravity problems that we did. And so somewhere right about here is 810. Again, I'm not being super precise. And if we sell 810 units, the slope of this line, which is r prime of x, would be equal to 3. So the derivative is a line, right? It's linear. It's clearly linear. Look at the equation of it. Yeah. And it is increasing at a rate of $3 per unit. And you can watch what happens, just sort of intuiting what happens. Your revenue is increasing until it gets horizontal, and then your revenue stops increasing. This is a very important point. We call it a critical point. So when it reaches that maximum, watch what happens to your revenue. Your revenue will start decreasing, and that's bad. So we're going to keep our eye out on this point right here. And in the next example, we're actually going to make a little bit of money, at least, fictitious money, academic money here. You cash out on this later in life, right? By introducing the concept of profit. Well, I guess introducing is the wrong word. You've already been introduced, but maybe I should say welcome back, profit. So suppose the profit of a particular product is given by you'll notice the key difference between profit and revenue is that profit has a constant term that's always negative. Right. Revenue only has the first two terms. Profit has this constant term that's negative. We call that the overhead, which means that you don't start at zero. Revenue starts at zero. Profit actually starts, we say, in the hole. Yeah. You're in the hole $2,500 until you start selling stuff, right? And then you have to sell a certain amount just to get out of the hole. So profit is a little bit more dangerous. Yeah, it's a little bit harder to get out of the hole with profit. So this includes cost, yeah, where X is the number of units produced and sold. That's the key. All right, so produced is cost, sold is revenue, and when you combine the two, right, revenue minus cost, you get this, you get the profit. Find the number of units that would result in a maximum profit. That will result in a maximum profit. So again, number of units produced and sold, that will give us the maximum profit. All right. So intuitively, you're sort of thinking about it like this. You're starting off way down here at negative $2,500. That's where the graph starts. You start selling stuff, and you want to get to here where the profit is maximal. All right. Why did I draw that horizontal line? Because that's the slope where the profit is maximal. So the question is, what is this X value where the profit is maximal? So down here, we call this the hole, or in the red, until you breach the x-axis, and then you get into the black. You're starting to make profit, and then you make your maximum profit, and that's where you want to quit. Yeah, you don't want to keep going, because if you keep going, your profit actually goes down. So your goal is always to hit that maximum. All right, well, this is calculus, so let's do some calculus. P prime of X is the limit as H goes to 0 of negative 0.11 X plus H squared plus 90 X plus H minus 2,500. This is going to be tough. I'm going to need more space. Just scooting over to make some more room here. Negative 0.11 X plus H squared plus 90 X plus H minus 2,500 minus, and then I put this entire function of profit in the second set. 90x minus 2,500 all over H. So that's the limit as H goes to 0. 0.11 X squared minus 0.22 xh minus 0.11 h squared plus 90x plus 90h minus 2500. Watch this trick. When I run out of space, I can go like this. When I distribute this negative, that's going to become a positive 2500. So those are going to cancel. That's going to become a negative 90x. Those are going to cancel. And that's going to become a positive 0.11 x squared. And those are going to cancel. And then I can go to my last step. Dividing everybody by h. All right, so just a little technique. You know that these last three terms, when you do this definition, always cancel. So I'm just going to put them underneath where they cancel as sort of bookkeeping, just to keep track of what got canceled. And then I'm going to get rid of all these h's. And remember, the middle h goes to 0. So I just get the leading h, or the leading x, 0.22x, negative 0.22x, and then the constant plus 90. Now, this doesn't tell me the answer. I probably shouldn't be boxing this yet, but I'm boxing it just for your notes. This is the derivative. It's the derivative of profit. So this is P prime of X. That's our derivative of profit. So if I want to know where it's maximal, max profit occurs when P prime of X is equal to 0. So go ahead and set this thing equal to 0. And solve. I might have to round. I don't know what's going to happen here. Negative 90. Unlike the last one, this one I didn't predict in advance. Sometimes I like to plan things out. Sometimes I just like to throw caution to the wind and see what happens. It's just like anything else in life, you know. You gotta go for it every once in a while. So I get 90. This is a negative divided by a negative, so the negatives are going to cancel. Divided by 22 hundredths, which is 90 times 100 22nds, which is 9,000 over 22. I don't feel like getting up and grabbing my calculator. I want to sort of feel what my grandparents had to feel, you know. No calculators in the old days. 22 goes into 90 one time. I know, if you have a calculator, you already know the answer. You're like, Dr. Jordan, stop. What are you doing? Oh, it goes in way more than one time. It goes in 4 times. 22 goes into 90 4 times. So that's going to be 88. 22 goes into 20 0 times. 22 goes into 200 5 times, 6 times, 7 times, 8 times, 9 times. 9 times 2 is 18, carry the 1. 9 times 2 is 198. Remainder 2. So we're going to say approximately 409 units. This is rounded. So this is rounded to the nearest whole number, 409 units. I thought about rounding to 410, but the remainder is too small. Yeah. This is 409 point. It's not 0.2. It would be it'd be 0.0. Yeah, because look, 22 does not go into 20, so I know that the decimal value is less than a 0.5. So I'm just going to round it to 409. Now, if this was 409.5 or 409.6, I know this is calculus. I don't need to tell you this, but sometimes when you get this far along in math, you forget the 5th and 6th grade rules that we learned when we were children. So there it is, 409 units. It's pretty darn close to almost exactly 409. All right, so that's our business calculus for the day. There's your dose. You've been duly business calculized. Let's get back to the just general math. We have a lot to cover in the remaining time that we have together. So a couple more objectives. Back to the tangent lines. We've been talking about the slope of the tangent line, but we haven't found the equation of a tangent line yet. Remember, the slope is just one aspect of the tangent line. So I want to make it very clear. If I say find the equation of the tangent line, I need a little bit more than just the slope. I need a little bit more information than just the slope. So let's get into this. So first we need slope. Yeah. That'll be f prime of negative 2 because my x is negative 2. And the y-intercept, which is b. All right. Now, I don't know if you remember the formula for it, but I'm going to do a little cloud here. Y equals mx plus b. And so that means b equals f of negative 2 minus m times negative 2. In other words, b is y minus mx. Right? So we need to find both of these things. Now you could just carry around this formula in your head. That's the only one you really need. And then once you have this formula in your head, you could always figure these ones out later. I like to just start the process going, oh, what am I looking for? I'm looking for the derivative at negative 2, and I'm looking for the y-intercept at negative 2. Right? Or the y-intercept of a line that passes through x equals negative 2. All right, the slope is really the calculus part of it. So f prime of negative 2. Going back to the first example, I like using the option 1. There's my option 1. So the limit as x goes to negative 2 of f of x minus f of negative 2 over x minus negative 2. This is the quicker of the options. Okay. I do need to know what f of negative 2 is. So I could do a little bit of scratch up here. It's not a bad idea just to get the scratch work done ahead of time. It's always just basic arithmetic. 4 minus 16 is, what's that, negative 12 plus 10 is, oh, negative 2. Coincidence. That's not going to happen very often. So f of negative 2 is this time negative 2. It just means that the line happens to pass through the point negative 2, negative 2. Again, I didn't even plan that. I just randomly picked an x, I plugged it in, and that's just the way the cookie crumbles here. I do like to double check when I see coincidences that were unplanned. Yeah, it's true. All right, and then you've got x minus negative 2, which is the same as x plus 2. So we've got the limit as x approaches negative 2 of x squared plus 8x plus 12 over x plus 2. Remember, the denominator gives you a clue as to what the factors are going to be. One of the factors must match the denominator. So it's x plus 2. So the other factor is x plus 6. Oh, we've seen that before. Totally different problem a while ago, but we saw the same kind of thing happened. Another coincidence. It's a day of coincidences. So there we go. That's our limit. So now we're going to take the limit as x approaches negative 2 of x plus 6. So that's going to be negative 2 plus 6. And so the slope is 4. That's my slope. All right. So we got the slope. Check. And now we need the y-intercept. So B is the y-intercept. That's going to be f of negative 2 minus m times negative 2. So f of negative 2, again, was negative 2. That's a coincidence. Minus m. This is your m. So that's 4 times negative 2. So that's negative 2 plus 8, which is 6. And then we put these two together, and our answer is y equals mx plus b. So this is the equation of that tangent line to this function at that point. I am going to bust out the grid in a little bit and try to do some detailed graphs. This one was a pretty quick result in finding the slope. It used that simpler version of the derivative, but just for the sake of it, I just want to show you without using the grid. X is negative 2. Coincidence that y was also negative 2. And then we have this line, 4x plus 6. So 1, 2, 3, 4, 5, 6. So this line passes through here and here. So this is y equals 4x plus 6. That's the tangent line. All right. So where's the graph? That's an interesting question. You don't see the graph, do you? But you kind of can. Look, that's the whole point of the tangent line. The tangent line kind of gives you a little snapshot of what the graph looks like. So this shape is your f of x. And so I hope, if anything, I mean, I want you to get the right answer. Yeah, and I want you to pass the class. Sure, all those things matter. But what's much more important is when you get these answers, how they give you so much more information about what is actually happening here, right? So everything should line up. Look, there's the slope. It's 4. That's pretty steep, right? If you remember one of the earlier examples, we said the slope was like, I don't know, what was it, 18 or something? I mean, if this is 4, this is a slope of 4. Could you imagine what a slope of 18 would look like? I mean, it would be like, it'd be almost vertical, almost. So you kind of, each time that you get a result, that result is sort of enriching your understanding of what's going on, right? Yeah, or not, or you just get an answer and move on to the next question, and off you go. You know, that's really more of a personal choice. So that's about, I don't want to say that's it for derivatives and tangent lines, but that's all I have for this particular exposition. There are other notations for the derivative. Well, there's in particular one other notation for the derivative. When an equation or when a function is written using x and y, so a function is written using x and y, the derivative is written dy dx. And the way we read this, so this means f prime of x. So this is the derivative of y, and then we say with respect to x. So the way we read this is the derivative of y with respect to WRT x, with respect to x, dy dx. All right. So note, if y is a function of x, then dy dx is just another way to say f prime of x. Which I hope really kind of makes some intuitive sense. In algebra, we spend a great deal of time, or I know I spend a great deal of time, convincing my students that y and f are the same thing, right? Sometimes I call it y, sometimes I call it f of x, right? They're interchangeable terminologies. Well, in calculus, I will spend a great deal of time convincing you that these mean the same thing. Sometimes I will say dy dx, and sometimes I'll say f prime of x. The derivative of y with respect to x is the same as the derivative of the function f of x. Why would we need that type of thing? Well, you know, just like anything else, we like to have different notations. Sometimes I like to not use the letter f. Right? I want to sort of have the ability to move away from the letter f. Okay, so let's do an example. I don't know, what am I up to? I haven't done very many today. Example 5. Negative 6x squared minus 2x minus y equals 7. Find dy dx. So find the derivative of y with respect to x. Well, the first thing I need to do is rewrite y equals an expression a function of x. I could say expression, but I want to write it as a function of x. Right? So I need to get all of my x's onto the other side. Get all my x's onto the other side. Or I could just move the y to this side. It really doesn't matter. I'm going to go this way. 6x squared. No, I'm not. I changed my mind. I would rather just move the y. So much easier. That's so much easier. So the goal is to isolate the y. So it doesn't really matter what side you end up on. Now I'm going to move the 7. So I want y all by itself. Oh, I already moved it onto that side. So I've got negative 6x squared minus 2x minus 7. So now I'm ready to take the derivative. I am right-handed, so if I do solve an equation backwards, I like to switch it around so that my y is on the left and my x's are on the right. It's mainly because I read from left to right, you know. You could read it from right to left, you know, and you'll still get the same result. It'll just read backwards. It means the same thing. A tomato read backwards is still a tomato. Tomato. I don't even want to try to read tomato backwards. All right, so let's do it. Dy dx is the limit as h approaches 0 of negative 6x plus h squared minus 2x plus h minus 7 minus negative 6x squared minus 2x minus 7 all over h. So that's the limit as h approaches 0 of negative 6x squared minus 12xh. I got to give myself more room. The limit as h approaches 0, negative 6x squared minus 12xh minus 6h squared minus 2x minus 2h minus 7 plus 6x squared plus 2x plus 7 all over h. You might notice this is exactly what we've done in every one of these derivatives. It's just that we're not using the letter f anymore. You know, everything is just x's, y's, and h's. So let's cancel those guys, cancel those guys, cancel those guys. I feel like I've seen this show before. It's because you have. Cancel the h's. So this is the limit as h goes to 0. Negative 12x minus 6h minus 2. And so now when you take the limit, the middle term will go to 0. And you will get negative 12x minus 2. And that's it. So that is your dy dx. So if y is equal to negative 6x squared minus 2x minus 7, then dy dx is negative 12x minus 2. I like to write these next to each other so that we can start to recognize patterns here. In one of my future videos, it might be the next one, it might be the one after that. I don't know how much farther I'm going to get. But it's coming soon. You might already see it. I don't know. Everybody's had a different experience in life, in mathematical life. But if you already see it, then you kind of know where I'm going with this, right? We want to establish some patterns that will give us a much faster way of going from here to here, right? And if you already see it, that's great. I'm going to save it for a future lecture, but it's staring at us right here. There's a very distinct pattern that's going on. I'm just going to do a couple more of these, and then we'll wrap this up for today. To me, it feels like today never ended, because it's just continuing right on where we left off with this derivative. So it's been a heck of a day for derivatives. All right, so let's do example 6. So let's do xy minus 3y minus 12 equals 0. Find the equation of the tangent line at x equals 4. All right, so we got a lot of work to do today in this example. First thing we have in terms of x and y, so we need to find dy dx. Right, that's our first step. That'll be our slope. Right? Then we need to find the equation of the tangent line once we found the slope. So we'll go ahead and wait on this. We don't need to do that right away. I've been lecturing on this for so long, all my black pens are running out. So I'm going to go ahead and do this one. So I've got xy minus 3y minus 12 equals 0. I need to find dy dx, which means I need to isolate the y. All right, I got to get y all by itself, so I'm going to factor out the y. Quick review of two-term factoring called greatest common factoring. These both have the same factor of y, so I pull it out to the front. Even though there are two of them, remember the principle of factoring? This is like the distributive property. This y appears in both factors, so I only need to write it once. Then I divide both sides by x minus 3. All right, now I don't really need the parentheses anymore, but it wouldn't hurt to keep them. They're optional at this point. So this is my y. Okay. Now I need to find dy dx. Don't forget x equals 4. Let's save this down here. X equals 4 because I'm about to erase it. So I've got y equals 12 over x minus 3. So dy dx is the limit as x approaches, or as h approaches. I'm doing option 3. Actually, I only care about this one point, 4. I'm going to change my mind. I'm going to do x approaches 4. Might as well. I mean, I'm not going to need another value, right? I just need one single result. So if I only need one single result, this one is much easier, right? So it'll be 12 over x minus 3 minus 12 over 4 minus 3 over x minus 4. It is a little messier at first, but it doesn't have the H, right? That's the advantage of this. It's just getting right to the point, x equals 4. So x is approaching 4, and it's just like I'm laser focused on that one answer. So the limit as x approaches 4 of 12 over x minus 3 minus 12 over 1. I like to write it like this. Old school, divided by x minus 4. Yeah. It's just, it makes the fractions a lot easier to deal with. So I get the limit as x approaches 4 of 12 minus 12 times x minus 3 all over x minus 3 times 1 over x minus 4 double checking my math here. I did that pretty quickly. It's just a common denominator. Because this term only has a 1 in the denominator, the common denominator is just x minus 3. So I only had to multiply the second term by x minus 3. I do a quick breath to check my arithmetic. So I've got 12 minus 12x plus 36 over x minus 3 times 1 over x minus 4. Which is the limit as x goes to 4. Oh, so I've got 12 minus 12x plus 36, which is going to be negative 12x plus 48 over x minus 3. I'm going to go ahead and just put the x minus 4 back down here in the denominator. So in other words, I'm multiplying the top by 1. Yeah, nothing happens to the top. And I'm multiplying the bottom by x minus 4. Just so that I can get rid of this sidebar here, the sidecar here. Now I'm going to factor out a negative 12. And there it is. If you don't get a matching pair, then you know you did something wrong. See the x minus 4? It has to have a match. Otherwise, you've done some arithmetic or algebraic error. Coming on up here, I've got the... I'm going to have to come all the way up here. Hold on. So dy dx, derivative of y with respect to x is the limit as x approaches 4. I'm just going to copy all this down. Negative 12 over x minus 3. Parentheses are optional. I could put them on the bottom. I could just get rid of them altogether. They don't really matter at this point. I'm going to plug in 4 for x. Yeah, so once you've canceled the x minus 4, there's nothing preventing me from just evaluating the limit. So now the limit as x approaches 4, direct substitution, just plug in 4, and I get negative 12 over 1. Yeah, which is just negative 12. So there's my slope. So If I did not just need one slope, if I needed other information, then that would not have been the way to go. I would have had to do a little bit more work to find a derivative in terms of x, right? I should mention, since I didn't do it this way, if I used option 3, the limit as h goes to 0 of 12 over x plus h minus 3 minus 12 over x minus 3 all over h, blah, 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 a lot of work. But I'm already over an hour now, so I'm not going to do it. I already have my answer. It's negative 12. This is what I would have gotten. For those of you that are curious, what about the other option? Would that have worked? I remember, teaching this class in a classroom, and that's a very common question. What if I would have chose one of the other options? This is what you would have got. Now, would you still get a slope of negative 12? Well, look, dy dx, negative 12, plug in the 4 minus 3. The only difference doing it this way is the denominator now is 1 squared, but 1 squared is still just 1, and you still get exactly the same result either way, okay? So I just put sort of dot, dot, dot. This is a lot of work if you would have chosen option 3, but it still would have given you the same result, all right? I'll leave that out there as a curiosity quest for yourself, all right? So now we need b. Remember, b is y equals mx plus b. Yeah, so b is y minus mx. All right, here's our original function. So I've got 12 over x minus 3 minus negative 12 times x. Does anybody remember what x was? It was 4, right? Yeah, right here. X is 4. So this is 12 over 4 minus 3 plus 12 times 4. So b is 12 plus 48, which is 60. So I've got my m, I've got my b. And so my final answer is the equation of the tangent line at x equals 4 is y equals m x plus b. B is 60. And there you go. So now you've seen derivatives multiple ways. You've seen tangent lines multiple ways. You've seen equations done in pretty much the same way. This doesn't have the notation of f, right? I did this entire problem without ever saying f of x. Did it all using x's and y's. But you still get the same result either way. I'm going to have to end with one more. This is going to have to be the last one because I can see my time is running out. Instead of finding the equation of the tangent line, let's just end off with one more derivative. Let's do another dy dx, but we'll stop when we get to something like this, right? Without actually plugging anything in at the end. That's about all the time that we have left for today. So example 7, given, let's do a nice square root function. We haven't seen one of these today. Just find the derivative dy dx. All right, and that should do it for today. Give myself some room here. So the limit. Now, if I'm finding dy dx and I don't have an x value, the problem is not asking for any particular x value, then I really only have one way to do it, and that's the third definition or the third option. Right? You can think of it all as the same object with 3 different ways to define it. So the limit as h goes to 0 of the square root of x plus h plus 5 minus the square root of x plus 5 all over h. That's the limit as h goes to 0. Now, it'd be nice if you could just plug in 0 now and be done with it. Yeah, and I would say, have a good day. See you on the internet, right? But no, it's not that easy. Because if you plug in 0, you end up with dividing by 0, and that's not allowed. So we're going to have to do a little bit of algebra. You've seen these steps before. You multiply by a special form of 1. So you copy the numerator and the denominator. And then you change the middle sign. All right. When you're doing a derivative, that middle sign is always negative. It's just part of the formula. So that means this one's always going to be positive. I do sometimes say, well, if this one was positive, then that one would be negative. And that is true. But when we're taking derivatives, this is always a minus because it's the definition is always subtraction. So that means this one will always be plus. You don't do anything on the bottom. All right. I don't want you to spend, sometimes I get emails going, Dr. Jordan, I spent 10 hours on this problem and I want to say, why? Why? Don't spend 10 hours on it. Just don't chase yourself around in circles. Just leave the bottom alone. Spend 10 hours on the top if necessary. So you're going to get, that's going to cancel. All right, you've seen this before. Square root, x plus h plus 5, square root, x plus h plus 5, those cancel. The middle terms always cancel, so I'm not even going to do them. And then I'm going to do the last term. Yeah. These are what are called conjugates. So one of them's a negative, one of them's a positive. So that's always going to be negative. And then the square roots are going to cancel again. Now you do have to be careful. When the square roots cancel, you should leave behind a set of parentheses. All right. If you forget these parentheses, your answer will be wrong. So the way I have it right there is technically incorrect. All right. You got to have parentheses there. Technically, there's parentheses here as well. Yeah. These are called non-essential, the ones on the left. If I remove them, there's nothing wrong with the answer. The ones on the right are essential. If I remove those parentheses incorrectly, it would be wrong. At this point, I'm just going to remove all the parentheses. So I have x plus h plus 5 minus x minus 5. So that's why these are essential, because of that negative. Leave the denominator alone. Leave the denominator alone for now. Do some canceling. X, negative x. 5, negative 5. Oh, H. And then put an invisible 1. There was already a 1 in the numerator. Right? You just couldn't see it. And then once you cancel all of these terms, then it becomes clear that there's a 1 there. And he's like, I was here the whole time. You just didn't see me. Right. And now let's take the limit. The limit as h approaches 0. Now you can go ahead and plug in 0 for h. And you're going to get 1 over 2 times the square root of x plus 5. All right. And again, it's a big 2. It's not a little 2. It's not an index of 2. There actually is an index of 2. It's right in here in that little crook of the square root. I don't know if you can see that. I don't typically write it. Most of us don't at this point. It was very common in the 20th century to write it. I think it's interesting that, the iPhone didn't even exist in the 20th century, but when you take your iPhone and you use the calculator on your, or whatever smartphone you have, it still has the little 2 in the crook, the little 2. But we stopped using that. Most of us stopped writing it, 30 years ago or so. So I do remember when it was there all the time. All right, so this is a big 2. I don't really have room here to justify that, but it's like there's an invisible 1 out in front here. There's another invisible 1 out in front here. And these 2 invisible 1s, when you add them up, they become a 2. And you have 2 of these square roots. Okay. That's all we have time for today. I hope that you are keeping up with the material. Feel free to email me if you have any questions. But until my next video, keep working hard. I'm Dr. Jordan, and I'll see you on the internet.